now that we've made scatter plots of our data, now it's a question of how well does that data fit a linear relationship. So we were just using our opinion before by looking at it to say whether it was positive, negative, or maybe not. But there has to be some kind of measure. So typically you look at what's called the Pearson correlation coefficient, Pearson being the guy that figured it out. So if you have all the data, it's a population obviously. They like to use Greek letters. So they use rho as the Greek letter. I don't know, I should have put that in there, right? RHO for the population. They use lowercase r for the sample, right? And what the correlation coefficient tells you is not only how good the model is in the quality, it also tells you the direction. So that's the two things that it tells you essentially. So the value of the correlation coefficient is between -1 and 1. So you technically can't get 1 or -1 unless it's perfect, and technically can't get 0 either. So it's kind of asymptotic, and you can't really get there. So the closer to 1 you are, it's a better positive model. The closer to -1 you are, it's a better negative model. So it's a question of at what point is it high enough positive or high enough negative to be considered a linear model. And we'll do some inference testing and confidence intervals later on to show at what point is the R value, correlation coefficient, good enough essentially, right? Because obviously getting close to 0 is bad. You know, it's not a really good model. So if I'm going to estimate what the R value is, so if I look at these graphs here and I estimate what the R correlation coefficient is, I don't know. So definitely, if I go left to right, this is positive. It's not perfect, obviously. So maybe somewhere in the 80s, maybe like 82, 83, something like that. That sounds pretty good. This one's definitely negative. It's almost perfect. So I don't know, maybe -97, 98, something like that. That might be good. This one's a positive one. It goes left to right up. It looks pretty good. It's definitely not as good as the last one. Maybe somewhere in the 90s, 90, 91, 92, something like that. This one's going down. It's definitely way worse than this one. It's worse than this one, but it's negative. Maybe like -74, 75, something like that. This one's going down. It's definitely better than this one, but it's worse than this one, so it's somewhere in between. I don't know, 85, 86, 87, 88, somewhere in there. And again, these are all rough guesses. And this one's going up. It's positive. It looks pretty good. I don't know if it's as good as this one or not. Maybe worse. I don't know. How about 96? That sound good? All right. So besides estimating, because we observed visually the graphs and we made a guess as to what we thought, and we're observing here and we're guessing as to what we think R is. What about the exact calculation? So the exact calculation is using the sums of all the data essentially. So I'm going to copy this to the spreadsheet. So what I did is I put all the data in here, and I put the x times y, x squared, and y squared here, which are the things I'm going to need to calculate the R essentially. Okay. All right. So the things we need to do are n equals and R equals, and then shift this to the right. Okay, and we'll copy this all the way down, paste, and paste. So I have all three of my data sets here in the 12-3 tab. Okay, so x times y is x times y, right? This is always your x, your input, and that's your y, your output. And this is x to the second power. And then this is y to the second power. Then I'll take those and drag them down. Okay, we'll do the same thing with the other ones. This is x times y. This is x to the second power. This is y to the second power. And we'll take this and drag it down. And lastly, x times y. X to the second power, and y to the second power. Okay, so those are all the things that I need, but I don't really care about the individual values. I care about the sum. So I'm going to take all this right here, and we'll put bold, orange, we'll put the word sum here, right? And about sums plural, that might actually make more sense. And then we'll box this out and center it. How's that sound? All right, so copy, paste, and paste. Okay, so this equals to the sum of all of these things here. Then I'll drag it across. Okay, so this represents the sum of x, the sum of y, the sum of x times y, x squared, and then y squared sums, essentially, right? So we'll do the same thing here. We'll do the sum of all of these, and then drag it across. And then the sum of all of these, and then drag it across. Okay, so if you notice sigma of xy, this first little piece right here, so we kind of map out what we have and what we need, right? This is right here, right? Right, this x is right here, right? This y is right here, okay? X squared is right here, and then y squared is right there, right? Because it's the sum of all of them, right? So one thing we need to get is n. So 1, 2, 3, 4, 5, 6, right? It says 6 down there. So a lot of people will highlight all of it and say 12. It's not 12. It's 6 because it's 1 coordinate, 2 coordinates, 3 coordinates, 4 coordinates, 5 coordinates, 6 coordinates. Okay, so here's the trick to do this effectively in the spreadsheet, essentially. What you want to do, let's get this out of the way, is do an equals, parentheses for the numerator, divided by the square root, parentheses for the denominator, and then inside the square root you want to put parentheses times parentheses. Okay, because I have a couple parts here. I have a numerator, which is going to go here. I have an x part, which is going to go here. And I have a y part, which is going to go here, essentially. So don't try to do it left to right. Try to do it in groups. So, all right, so my values here are n times x squared minus x times y. All right, so that's the numerator part right there. Then we'll do the x part down the bottom now. So the x part is n times x squared minus x to the second. And that's where the mistake generally comes in, because people look at this and they think that this is the same as this. No, this is the squared of the x, right? See how it's on the outside of the parentheses? It's not the same thing, because this is x squared and this is x, right? So what I'm doing is I'm squaring this value, essentially, which is not the same thing as that. Okay, so the y part, right, is n times y squared minus y to the second. There we go, so 0.98. Okay, so I can go through and do there's a trick to this. So there's how many here? If I count this one, there's 7. And if I count this one, there are 10. Okay, so what I can do here is I can copy this, paste it here, right, and just remap the values, essentially. So what I want to do is remap it to 18. So 18, 18, 18, 18, 18, 18, 18. All right, so notice it's highlighting all these ones down here now. It might not be 18 for yours, but you can remap it. Okay, so that's some R value here, and we'll paste it again. Oops, copy. Paste it again. We want to map it to 31 because that's where the numbers are. So I'm going to map it to 31, 31, 31, 31, 31, 31, 31, and 31. There we go. Okay, just make sure you don't change like these ones here that map to the actual quantity in the formula. Okay? Alright, so we have a very poor positive value there, very good negative value there, very good positive value there. So I would say here is the car revenue data. The correlation coefficient is saying they have a very good positive relationship. The absence data is saying it has a very good negative relationship, linear. And then the teacher ratio problem has a positive relationship, but it's not very good. That's below 0.5. It's below half. That's not good whatsoever. Okay. So if I go back to my notes here, it says, what does the R tell you about the data set and how does this compare to the graph? Okay, well, in the first case, right, this is a good positive, a good fit in a positive, in positive linear, basically. Okay, so we go back to here, you only have 3 variations of what could happen, basically. Positive, whoops. There we go. Positive and good linear. So that's basically saying that that's going to line up with our graph. So if we go back to our graph as to what it looks like. Actually, no, the graph's not there. Sorry. Our graph is right here. And it's a good positive linear relationship. That's good. Okay, let's go to the next one. The next one is a good negative relationship, right? Because it's close to -1. This one's close to +1. If we go back and look at our graphs, that's a pretty good -1, right? So this is a good +1. That didn't work out so well. What happened there? Okay, come on. So that's a good +1. That's a pretty good -1. But this one, that's not very good at all. It's like a hump there. You know what I'm saying? So the last one, okay, the pupil problem, what we're saying there is this is not a very good relationship. Okay? Oh, I keep doing that. There we go. Okay? So it's either linear or not a linear relationship. We're not saying no relationship. We don't know that because we're only checking for linear. We have to check for other things, which we're not doing in this essentially.